Today I'll be presenting our paper, Crane Fast and Migratable GPU Passthrough for OpenCL applications. This is work with myself as well as Daniel Katz, who's in the audience, and other master's students at U of T, and my advisor, A.L. Villara. So GPU computing has entered the cloud. We see that in the form of GPU instances being offered by all the major cloud providers with a varying number of GPUs per instance. We also see GPU apps entering the cloud, such as video encoding and decoding, machine learning, training neural networks, as well as scientific computing, such as molecular simulations. We also see companies investing in heterogeneous computing. Semantic is training neural networks to identify security incidents in their products. Uber and Waymo both have self-driving car projects, which heavily depend on machine learning techniques to accelerate their training algorithms. So VMs are still a key ingredient to cloud computing. They provide useful functionality to developers. For instance, they provide checkpointing. By that I mean the ability to suspend a VM and resume it later. They've also provided us with migration, the ability to move a VM from one machine to another. That's useful if you want to perform machine maintenance, being able to move a running OS to a different machine, because then you can administer the physical machine by powering it off, etc. Also, you can consolidate multiple tenants onto a single machine. This can lead to power-saving opportunities, since you can turn off a machine once all the things have been moved off of it. It also leads to load balancing opportunities, allowing you to get the full cluster utilization. So a key question, though, is can we still have these useful tools if we're using GPUs in the cloud? So how do GPUs get used in the cloud? GPUs are assigned directly to VMs using GPU Passthrough. So what GPU Passthrough provides is very high performance access to the GPU by the VM. So how does it do that? What GPU Passthrough does is it provides unmediated access to the GPU from the guest. So what do I mean by that? What I mean is, when the guest interacts with the GPU, DMA operations to the GPU and from the GPU are unmediated. There's no ring buffer in the hypervisor that's used as a communication mechanism. It's all directly to the GPU. Also, interrupts from the GPU to the guest are sent directly to the guest. There's no hypervisor mediation. So the result is very high performance, close to the bare metal OS access to a GPU. So a question we now have, though, is without any of this hypervisor mediation, can we still have checkpointing and VM migration? Well, let's answer this question. So first, let me go over how migration works so that I can better describe the issue. So here's stop and copy migration. First, we're running on a source host, and we have a stop and copy phase. So what happens is the hypervisor sends a suspend signal to the guest, which triggers us to stop executing and to move device state to DRAM. Okay? So then the guest suspends, we move to the new destination host, DRAM is copied, including the device state, and then when we resume the guest, it triggers DRAM to be re-injected into the device, and then we resume on the destination host. So the key idea here is that there's two important mechanisms that go on in migration. First, we have to be able to safely interrupt interaction with devices in the midst of the guest executing. Second, we have to be able to extract on the source host and re-inject on the destination host the device state before it can resume execution. So let's come back to the original question. Can GPU Passthrough support VM migration? So let's try and do a simple experiment. Let's try and do something even simpler than migration. So let's try just detaching a GPU on a guest on one host and then reattaching it afterwards. So what does this look like? So first we send a suspend signal to the guest. So hopefully the GPU state will be written to DRAM at this point. So then we detach the GPU from the hypervisor, and we reattach the GPU. Then, after resuming the guest, it turns out the guest actually crashes. Okay? So what this is telling us is that there are no mechanisms to safely interrupt access to a GPU. Also, we don't have any mechanisms for extracting and reinjecting the device state. So what we have to do is we have to build them ourselves. So that leads us to Crane. So Crane provides GPU pass-through without sacrificing VM migration. So let's see what Crane looks like. When an OpenCL application runs, we intercept calls to the OpenCL API, and we track the GPU state in DRAM. Then, when a stop and copy phase occurs, and device state is moved to DRAM, Crane coordinates moving dirty GPU state that's still on the GPU into DRAM. Then, we execute the stop and copy phase. Once on the new host, we resume, re-injecting device state. Crane coordinates re-injecting the GPU state using OpenCL API calls. So, by orchestrating these techniques, Crane is able to support both stop and copy and live migration modes. So, by virtue of Crane's design, we have three important advantages. First, we have performance which is close to GPU pass-through. Second, we have vendor independence. So we are able to support both the current GPU models and future GPU models so long as they support the OpenCL standard. Third, this is a maintainable approach since we don't actually do any application, OS, or hypervisor modifications. And I'll show you how we achieve that. So here's the outline of our talk. First, we'll talk about OpenCL programming, just a brief overview. Then I'll show you how we support stop and copy migration. Then I'll show you how we can extend stop and copy migration to live migration. And then I'll finish with an evaluation. So there's two main programming models for GPU programming, OpenCL and CUDA. We chose to focus on OpenCL. However, in the paper, we talk about how we can extend Crane to support CUDA. So that's not an inherent limitation. So let's look at how the state of DRAM in the GPU changes as we interact with the OpenCL API. So first, the programmer creates a kernel. In this case, we're just adding two vectors of floating point numbers together and outputting a vector of floating point numbers. So first, the programmer has to create buffers. These represent regions of memory on the GPU. So they have to create both input and output buffers. Next, they have to queue commands in a command queue. In this case, they have to write input for the two vectors. So this causes DRAM to be injected into the GPU. Then, after we run the kernel, now that the input's on the GPU, it outputs the result to GPU device memory. So the programmer then has to finish by reading the output into DRAM. And that completes the overview. So the key idea here, though, is that all the interaction with the OpenCL API is occurring through opaque handles. So you can think of like a file descriptor with a file. That's an opaque handle. In this case, they have the handle for the memory buffers. So let's see how Crane can enable stop and copy migration. So the problem here is that the GPU driver is closed source. It cannot be modified. So we can't implement extraction and reinjection mechanisms in the driver. Instead, we have to introduce an interposition library. Notice this is a new component. There's no application modifications. And it's in this interposition library where we're going to implement Crane's mechanisms for tracking, extracting, reinjecting. So let's look at tracking while an OpenCL application is running. So first, the programmer creates an OpenCL program. And the interposition library interposes on this call and records the function arguments, in this case the source string. And then we return an opaque handle so that it's completely opaque to the programmer what's going on. They don't see what's going on. So the key idea is that all the state we need to recreate this program object and other OpenCL objects is stored in these shadow objects that we return to the programmer. So let's look at the events leading up to before migration begins. So the programmer is continuing, creating both input and output buffers. So in this case, when they write the input buffer, what Crane does is we interpose in this call and we record the writes to a cached copy in DRAM. The reason this matters is because before migration begins, we have to extract all the GPU state. So if the GPU device memory is already in DRAM, it reduces that stoppage time. Then the programmer runs the kernel, which outputs to the GPU. Now, this state is on the GPU, but it's not resident in DRAM yet. So we have to keep track of this by flipping a dirty flag in the buffer, in the shadow object. Now, it's at this point that we receive the signal to begin migration. So, first we have to extract any dirty GPU device memory to DRAM before we can begin migration, so we don't lose that state. So we do that. So it's important to note that all of these things are being coordinated using simple, portable OpenCL API calls. Okay, so after we've finished migrating, we have to recreate the objects and re-inject the GPU state. So we receive a prepare to resume signal, and we recreate each OpenCL object using the shadow objects. So, for example, for a memory buffer, we simply recreate the buffer of a particular size, and then we use the cached DRAM buffer writes to re-inject. So the key idea here is that for every OpenCL object type, we simply have to recreate it using the arguments that were stored in the shadow object. Okay, so that's stop and copy migration. So how do we support live migration? So what is the problem with stop and copy migration? The problem is the VM is suspended for the duration of migration. Okay, so we'd like to continue using the GPU as we're migrating. Okay, so what are the challenges with supporting live migration? Well, first, GPU pass-through, we can't actually have a GPU attached to a VM as it is migrating. The hypervisor won't let you do this. Let's say that we modified the hypervisor to let us do this. What is the problem now? Well, as the GPU performs DMA operations to the guest memory, since the hypervisor isn't mediating any of these accesses, we don't know when DMA buffers are dirty. That's a problem, since when we actually finish migrating, these buffers won't get copied and they'll be lost. Okay, so instead, what we're going to do is we're going to perform API remoting to another VM on the source host. This is a VM that is pre-provisioned with its own pass-through GPU, so we can forward calls to it. So, use our mechanisms for extracting state and re-injecting them into this proxy VM on the source host, after which we can perform API remoting. So by performing API remoting, we have continued use of the GPU during live migration. So before we can actually perform live migration, we have to extract GPU state and send it to the proxy VM. So this incurs stoppage time. We won't be able to perform API calls during this time. So first, we actually have to wait for any running kernels to finish. And then we also have to extract any dirty GPU memory. We also have to unload the OpenCL library, since we actually can't unload the driver, and we have to unload the driver before we detach the card. We also have to send the shadow objects to the proxy. So we can use multiple threads to minimize the stoppage time in this case. Then, after we migrate, we also incur some post-migration stoppage time. So in this case, the proxy has to send any dirty GPU state to the new destination host. So first we flush any commands running on the proxy, we receive dirty buffers from the proxy, and then we reload the OpenCL library and recreate the objects. Okay, so let's look at the evaluation. So first we look at some data parallel and micro benchmarks. So these are common algorithms that you would find in any OpenCL programming. Then there's two categories of GPGPU programs you care about. There's user-facing applications, such as the video encoder, where you actually care the most about the stoppage time that you incur before and after migration, because you don't want to reduce the frame rate too much. We also have batch processing applications, where really you only care about the total job time. So the percentage overhead during the pass-through mode is the most important. So for instance, if you had a 20-hour long job and you had a consistent 5% overhead, that would actually add an entire hour to your compute time, so that wouldn't be very good. Okay, so first let's look at overhead due to state tracking. So first looking at the micro benchmarks, we can see that the overhead actually ranges between 1% to 5% to even 10% for these micro benchmarks. Okay. So let's look at the macro benchmarks. So for the video encoder, it turns out that we have about 10% overhead, but I'll show you in the next graph that this is actually okay, since the frame rate is still acceptable for a user-facing application. For the batch processing applications, the overhead is actually negligible, which is a great result, since that's what we care about for batch processing applications. So for the video encoder, so first, this is on the source host, where we're executing in tracked pass-through mode. Then we incur stoppage time, and then we perform, this is when we're performing API remoting during the live migration phase. Then we incur post-migration stoppage time, and then we're on the destination host and we return to pass-through performance. Okay? So first, notice that the 12% overhead isn't, the frame rate is still just fine. You want basically 60 FPS for a video. Next, it's worth noting that during API remoting, since we're performing communication over a socket between the two VMs on the source host, we do have like only a 20.1 FPS. However, this isn't an inherent limitation of Crane. We could have used shared memory inter-VM communication optimizations. So this is an optimization for future work. See the paper for details. Importantly, the stoppage times for the user-facing application are less than a second, which is great, which means you'll have no buffering time in the video. Then, after we migrate, we return to pass-through performance. So let's just look at what's going on during these stoppage times, just out of curiosity to see where the bottlenecks are. So during pre-migration, we first start by waiting for any kernels to finish. So it turns out, waiting for kernels to finish is not the biggest bottleneck in the pre-migration stoppage. If you actually look to the 85th percentile for DeepCL, which has the longest running kernels, it's about 10 seconds. However, for the other applications, such as the user-facing application, the kernel runtime's 99th percentile is less than 10 milliseconds. Then we have to send any state to the proxy. It turns out for DeepCL, this is the largest bottleneck, but it is not the largest bottleneck for other applications. It turns out that for X264, where stoppage time matters the most, the bottleneck is actually for unloading the OpenCL library. Again, these are batch processing jobs, so they take a long time to execute. The stoppage times are quite insignificant in terms of the total execution time. So we're actually just going to focus on X264 for the post-migration stoppage time. So for post-migration, you have to wait for kernels to finish on the proxy, which again does not take long. Then you have to send an dirty state from the proxy to the guest on the node destination. Then we reload the OpenCL library, and it turns out that the bottleneck here is actually re-injecting GPU state. Finally, I'll finish with related work. So there's been lots of work on GPU virtualization. We see that in the form of a taxonomy, which includes front-end virtualization, where the GPU driver runs in the hypervisor, and the guest uses API remoting to forward RPC calls to the hypervisor. We also see back-end virtualization, where the guest runs with the GPU in GPU pass-through mode, but it cannot migrate. We also have hybrid virtualization, where the guest forwards calls to another guest. So we actually use a mixture of these approaches. So when we're stationary, we're actually using GPU pass-through mode, so back-end virtualization. And then when we're doing live migration, we're actually forwarding calls to the proxy VM. So there's also been work on virtualizing other pass-through devices such as NICs. So driver-level virtualization, we actually perform state tracking at the driver level. However, we didn't do that because we don't have access to the driver and we want vendor independence. Finally, for there's VM introspection approaches where you can actually track DMA buffers being dirtied just in order to support live migration by actually polling the DMA buffers of the guest and seeing when they get dirtied. However, we actually have to dedicate a CPU to doing this polling, so we didn't want to do that. So we've enabled GPU pass-through without sacrificing stop and copy and live migration modes. The advantages, again, GPU pass-through performance. It's maintainable. We didn't perform any modifications. And we have vendor independence. For future work, we'd like to extend this to CUDA. We'd also like to optimize live migration performance using inter-VM communication mechanisms. Also, since our approach for virtualization is at the API level, you can actually use this to extract GPU state on one GPU model and re-inject it on a separate GPU model. So this might be interesting for performing GPU reallocation in a cloud environment. With that, I'll take any questions.
So Systor, thank you. We have time for a few questions. So this idea that you can transparently track GPU state and then re-inject sounds pretty cool. So I wonder, besides live migration, have you considered other use cases? Maybe, I don't know, maybe you can do GPU preemption in a cloud environment and maybe you want to prioritize applications or something.
Yes, so I've been looking at kind of like cloud environments or cloud services where this would be useful. So for instance, there's batch computing services where you basically scale up a batch computing service by just spawning new VMs.
Right.
So what you might actually want to do is take an existing VM and reallocate it a new GPU, because you might be bound on the GPU, so reallocating all those resources might be wasteful. So live migration is really just a mechanism for moving to a machine with a different GPU that you want. Yeah, there was another one, but I forgot. Yeah, so it's really a mechanism for performing reallocation.
Okay. Any other questions? Okay, so let's thank the speaker one more time.